Thanks, Catherine. Welcome everyone to Warwick. So this session is only 45 minutes long. We have 4 speakers. I've told them they've got 10 minutes each. And for each of you, after 8 minutes, I will tell you you've got 2 minutes left, and I mean it. It means there's actually not very much time for questions, but we will take some questions. We'll try and take a single question at the end of each talk. So first of all, Ian, are you there? He is here, but I can barely hear him. Can we hear him in the room?
Can you hear me now?
So here we go. So the question, I don't know how many times we've all heard over the last few years, you're muted, right? So Ian's going to tell us about the view from the UK, in particular on SWIMMR. Over to Ian. 10 minutes. After 8 minutes, I'll tell you, right?
Yes, you should be seeing my screen, I think. Can you tell me if you can see some slides? Hello?
Right now, we can see a Warwick University slide. So
wait a minute. Wait a moment. I can see what I think I'm showing you, which is a slide saying ionosphere and thermosphere.
We can't see that.
Ah, okay. let me try again. Hold on.
You are viewing Ian McCrea's screen.
Let me stop. I'll stop this share and start it again. Hold on. Beg your pardon.
You'll be happy to hear we have two speakers in the room. That's it, Ian, you're on.
Right, finally. Sorry about that. Beg your pardon. Let me just go. So as Catherine said earlier, we started GNOSIS in 2019, and one of the first things we did actually before the pandemic hit was we held a space weather seminar. And I think it's quite important for us in the space weather community to connect ourselves with this space sustainability activity, because of course it's no news to any of you that all the satellites that we're talking about in these sessions are not really in space at all. They're actually embedded in the upper atmosphere, whose number density ranges from about 10 to the 16 to 10 to the 13 and below, depending on altitude. And not only in the neutral upper atmosphere, I should add, but also in the ionized upper atmosphere, in the ionosphere. And both of those media have effects on satellites in terms of communications in the case of the ionosphere and on orbits in the case of the thermosphere. And today I'm really going to talk about the thermosphere. The thermosphere is a naturally dynamic environment. It has asymmetries due to insolation, due to latitude. Wind and waves are a factor in the thermosphere, and there's a lot of external forcing of the thermosphere by things like magnetospheric storms, substorms, solar flares, particle entry from the solar wind, and so on. And so if we really are going to enter the age that we should be in of space traffic management and very accurate orbit prediction, we need to understand the thermospheric environment very well. And we're moving towards that. So in the early days, the thermospheric models that existed were based on monitoring of satellites. So the early monitoring of satellite orbits produced things like the King-Healy wind model, the GNOSIS wind model from the 70s. But since then, of course, we understand the upper atmosphere a lot better. We have all our incoherent scatter radar data. We have a lot of in situ data from satellites now. And so there is a really good set of first principles physics models to inform the upper atmosphere and the ionosphere. But nonetheless, I would contend that a lot of the progress that's been made in thermospheric modeling over the last few years is on the back of some of the data assimilation techniques that have been developed. So one of the big breakthroughs, I think, was the inclusion of accelerometer data from spacecraft in low Earth orbit. So things like CHAMP and GOCHE and now, I guess, SWARM as well, are helping to refine the models. So CHAMP in particular, which was in orbit for 10 years, really showed the variability of the neutral density over time and revealed significant discrepancies with models. And in particular, not just large-scale variability, but also small-scale variability. So one of the famous CHAMP results was the variability over the cusp spot, where passing over the magnetic pole or close to the magnetic pole, CHAMP was seeing the effect of the modulation of the neutral atmosphere in this area where there's intense field-aligned current activity and intense heating causing upwelling of the atmosphere on a very kind of local scale. Variable from day to day because it depends very much on geomagnetic activity. So this is a very hard thing to predict a priori with models. Now, Don said that I would talk about SWIMMR. So the first few slides are what I presented in 2019 when we had our space weather seminar. At the time, we were beginning to frame this program called SWIMMR. SWIMMR stands for Space Weather Innovation, Measurement, Modelling and Risk. And it's a big UK program, £20 million, funded across 2 research councils for space weather research underpinning operations in the UK. So our goal in SWIMMR is to put new models and new data sources primarily into the Met Office, because the Met Office is the entity dealing with the space weather risk and space weather forecasting in the UK. So we have 6 projects funded through STFC. A lot of them are actually on the data side. And we then have 5 projects funded through NERC, which are on the modelling side. And one of those, the one in red here, which we call SWIMMR N5, is to do with thermospheric modelling and satellite drag forecasting. And it's actually self-consistent with the ionospheric modelling package. So this is led by the University of Birmingham, with colleagues at Bath, Southampton, and it uses a self-consistent model of the ionosphere and thermosphere, which we're going to put into the Met Office. So this is based on a system called the Advanced Ensemble Electron Density Assimilation System. It's known as AENEAS. It starts with a physics-based model of the thermosphere and ionosphere, but it assimilates a lot of data, a lot of satellite data, in order to refine and update the models. You can see the thermospheric element of AENEAS in that slide. There are probably, by the way, either online or in the room, several of the people that are working on this project. So I apologize to them for not explaining it as well as they could. One of the things that is being done in SWIMMR N5 is the physics-based background model, which only goes up to about 600 kilometers thermospheric density, so that below that altitude, the atmosphere can be modeled as a continuous fluid. It is possible using established climatological relationships and some extrapolations from assimilation data to extend the lid of that model to about 1,500 kilometers. And if we do that, then we can include something like 98% of the orbital regimes where our satellites are. So one of the things that SWIMMR N5 is doing is assimilating these accelerometer data sets. And the project can in principle go even further. So we could take ground-based observations of satellite orbits, so TLEs, and we could then assimilate the differences between the modeled and the observed orbits of satellites as a way of updating our thermospheric model with kind of thermospheric anomalies. And indeed, there are models that already do this. So in the right-hand side, you can see a picture of the high-accuracy satellite drag model from the States, which was informed by doing observations of these large sphere targets. I think there are about 75 of them, and looking at their orbital perturbations. But now, of course, in the era of space situational awareness, we are rapidly revisiting lots and lots of targets in the space of a few days. So there is a lot of orbit data we could start assimilating into these models to make them better. And so it seems to me that the neutral density models have undergone an interesting evolution from a few early satellite observations where satellite orbits weren't revisited very much, through first principles physics, through things like assimilation of accelerometer data. And now we have the potential to go back with a whole lot more assimilated observed satellite observations and put them into the models. So that's the kind of thing that we hope the SWIMMR work will enable. And to do it well, of course, we need rapid revisits to key objects, especially after severe space weather events. So that really requires the dedicated use for tracking radar. Who has a tracking radar? Well, we have one in STFC. So our Chilbolton dish, 25-meter dish at Chilbolton, is already doing space tracking observations with the UK Space Agency. And my last little advert in this talk is of something that doesn't yet exist, but I think it's going to exist soon. And that is a proposal called the Chilbolton Centre for Space Situational Awareness, which we have put in to be funded under something called UKRI Themes, which is a future funding scheme, which hopefully will have some money next year. There is a theme in that program called Building a Secure and Resilient Planet. And while I'm not yet sure that we will get money for space situational awareness in that program, I'm now reasonably confident enough to start talking about the fact that we might. And so in that program, if we get the money, we would make some dedicated SST type improvements to Chilbolton, but we will also try to bring in some of that space weather work, building on what we've done in SWIMMR, and trying to get more and more of a database of satellite observations to assimilate into thermospheric models and improve them. And I think this ought to be a big future part of our connection through the Met Office into the new National Space Operations Centre. So that's where we're going, I think. And I've probably done my time already.
You've done your time.
We'll stop there. Thank you, Don.
Right. Do we have any questions in the room for Ian?
I can see there's something in the Q&A.
We'll get on to that in a sec. We're going to have one question from Stuart here.
Good morning, Ian. Stuart Eves here. With regard to the data that you're looking for, you referred to the external measurements of objects in space using radars, which obviously is a good thing to do. Would it help if there were more accelerometers on spacecraft as well?
I would say yes, but there are probably people in the room that know the answer to that better than I do. There are not that many at the moment, but I mean, these things have spent cumulatively, I guess, a few decades in orbit now. So there is a reasonable amount of accelerometer data that's being assimilated. But yeah, more data of all kinds is always helpful, I think. And this is probably not a domain where historical data from a different phase of the solar cycle is necessarily helpful. I mean, ideally, we'd have a good coverage throughout the whole of the solar cycle, which I think we've got to some extent, but yeah, we need more.
Thanks, Ian. And there's a question online from Angela Mathis. Ian, great projects. Is the data available to UK or other industries, and will the results be published?
The SWIMMR stuff is the data is publishable. That's a condition of it. And I'm sure that the thermospheric modeling work in SWIMMR will be published in the open literature, probably is already being, and the results will be available through the Met Office. So yes, I mean, for sharing with the whole kind of community, I don't think there are any restrictions on that. With the future SST stuff, again, it's public funding, so I would assume it will be the same way, but we don't actually yet know that that project is definitely going ahead. Hopefully I'll be able to tell you more in a year or two's time.
Can I just butt in with a very quick question myself? So Ian, these models that you're producing in N5, they're effectively close to real time or retrospective. Is there any chance to do a forecast from a weather event?
Yes, so that's the goal, I think. I don't know whether there is a Birmingham or a Southampton person in the room that wants to say any more.
It sounds like a coffee time discussion. Anyway, sorry, thanks, Ian. That was a good talk. Enjoyed it.
Thank you.
Speak to you soon. So moving on to our next talk. This is going to be this is the view from South Africa now. So it's Leanne McKinnell. Hi, Leanne. Nice to see you as a well, I'd like to say in the flesh, but of course it's not in the flesh, but it's good to see that you're a real person after all. So Leanne, you're going to talk about the view from South Africa. So over to you.
Thank you very much. And I just want to confirm that you can see my slides.
Yep.
Okay. Thank you very much, Don, and thank you very much for inviting me to participate in the conference and for accommodating me on a hybrid platform. So yes, I'm coming to you from South Africa, and the intention, I believe, in having me present in this session was to discuss space weather, but most importantly to discuss an international perspective on space weather and where we in Africa are going with building our space weather capability. And I will try to do my best to stick to time. I just want to make sure that you can actually see the slides in presentation mode, because I can't see them at the moment. If I go like this, there we go. There we go. Okay, so that should be better. Don, can you just confirm? All right. I think
Yes.
they are.
Yes.
Thank you. All right. It's always a little bit tricky when you're managing the technology, although this hybrid platform is working very well. So my presentation is around space weather from an African point of view, and I've subtitled it Part of the Quest Towards Space Sustainability, because I know that's the conversation that this conference is really built around. But I do believe that space sustainability cannot be discussed without the discussion around space weather. So I'll just cover a little bit about space weather and why we should care, and then most of my presentation is going to be focused on the capability build for Africa in this area. So I don't need to tell this audience about space weather, but I just want to emphasize that we are really taking part in the conversation around space weather being a global challenge. Sorry about that. Space weather being a global challenge. And one of the main concerns that we have is the influence that space weather can have on the performance and reliability of our technological systems. And we are very interested in the regional impacts in Africa, particularly in terms of how solar events are affecting our ability to manage our technology systems. So although much of our conversation will be around satellites and space-based data, it's the ground-based data that is really giving us the perspective we need on space weather from that point of view. We in South Africa, we've been focusing a lot on ground-based effects. So looking at the aviation sector, looking at long-distance pipelines, looking at navigation, which of course is dependent on satellite technology, but affects so much of our infrastructure, particularly the infrastructure that is currently being installed in Africa for communications and navigation. So the vulnerabilities around space weather effects created within those systems is what is really dependent. And then I want to just throw in this slide, which I think is very interesting, sort of on the economic impact of space weather. So how much does space weather have the impact, the potential to impact our economies? Now, those of you who are familiar with the South African situation at the moment will know that energy blackouts is a huge concern here in South Africa. We don't need any more reasons for losing our ability to provide power to people. But so energy and the impact that space weather has on energy is one of the biggest concerns that we're looking at. We're also looking at a GNOSIS capability. So looking at how does the space weather impact our navigation systems, but also the economic repercussions that come about from having a vulnerable navigation system, a positioning system. And then, of course, security and transport being also in industries that are severely impacted by space weather. So all of these things, which are very familiar to the people in the room, led towards a 3-year project that we've just concluded, where we were building a capability for space weather in Africa. What does that look like? Well, South Africa's position in the space weather community really started way back. But in 2007, we became a member of the International Space Environment Service, looking at how do we identify what the regional impacts from space weather could be over the African continent. We opened our first regional warning center for Africa in 2010. It was a limited focus research and development center focusing very much on forecasting and predicting the impacts created in high frequency communications from space weather events. This center was upgraded again in 2018 after serving users very successfully on the African continent for 8 years. We upgraded it partially in terms of an IT capability, but still focusing on HF. In 2018, we were also designated through a submission from the South African government to be the space weather information provider for aviation and other sectors. So between 2019 and 2022, we rebuilt our capability as a space weather regional warning center for Africa. And I'm very pleased to announce that on the 3rd of November this year, we opened our 24/7 operational space weather center, which is, I'm going to tell you a bit more about in a moment, but is the only one of its kind on the African continent. So what does it mean for us? So in terms of the capability, we took to heart our international designation as a regional information provider, and our ambition is to be able to provide space weather solutions for the African continent, looking at the whole research to operations value chain in the domains of navigation, high frequency and satellite communications, and radiation exposure, with an emphasis on the impact, the regional impacts for the African continent, and how does that impact our technological systems. Training, interpretation, user requirements are also very much part of what we do. Many of the users that we're working with are not aware of space weather impacts and not aware of how the technological systems that they're so dependent on can be affected. So we, as SANSA, as the designated representative for South Africa, is now in a position to enable the mitigation of the risk created by space weather. And sorry, I should have said this at the beginning. So my home institute is the South African National Space Agency, and it's the space agency that is designated to be the provider of space weather information and expertise for South Africa, and then also representing the African continent.
2 minutes, Leanne.
Thank you very much. So in terms of space weather solutions, this is just a list of the space weather solutions that we are now in a position to provide to our users. And as I mentioned, the research to operations value chain is extremely important in terms of provision of these services. From an African perspective, so Africa's response to a global challenge, I've mentioned the member of the International Space Environment Service. We also provide representation on various expert groups on space weather. And we also are increasing our ground-based data throughout Africa so that we can have regional data that is able to be piped into an operational space weather center. So our African instrumentation network has now been extended. Our most northernmost instruments sit in Nigeria. And between Nigeria and South Africa, we have a wide range of instrumentation now and sensors to give us the data we need. And just as an example, and one of my final slides, an example of one of the space solutions that we've developed by increasing our database across Africa is a solution called Afritech, developed between SANSA and the Nigerian Space Agency, looking at a solution for navigation applications across the African continent, utilizing ONUSOND and global navigation satellite systems scintillation data to provide a African map for total electron content. And that's one of the products that goes into the forecasting sector. And then finally, so in conclusion, we have identified the vulnerabilities within our technological dependencies caused by space weather. We are addressing the operational capability as a service to the African region, but also in terms of addressing the research to operations value chain for space weather. We will continue to utilize our existing capability and our global networks. So our international participation is incredibly important to us, and we value our international partners who have supported us, including the UK Met Office and the University College London, in terms of making sure that we can get to the capability levels that we want to. And we are partnering with various role players, both on the research and the operations side. We have set up user networks within the African continent as well to make sure that everybody is ready to be able to use the information that can be provided. And thank you very much. I hope that was of interest, and I'm happy to answer any questions or to share more information outside of this forum. Thank you.
Thank you, Leanne. Very interesting. So do we have any questions in the room? We have a question here.
Morning, Leanne. Thank you. It's a very clear presentation. My name's Andy German. I've often done things around the applications of space data and what we do with it. So I'm interested in where your warnings would go. So if you detect a problem at the operations center, what do you do with the information? And I'm thinking about flooding, because every time globally there's a flooding event somewhere, a couple of days later on LinkedIn, you see all these warnings that were given and then nothing happened. So I was wondering, from a space weather perspective, what's your view on how prepared and ready the operations sides are?
Thank you very much for the question, Andy. Yes, this is a very interesting question, and one that we spend a lot of time with our users on. So I'll answer the last part of your question first. I don't believe that the users and the operators are as ready as we need them to be yet. There's always a question of what do you do with the information once we send it. So from an operational space weather center point of view, we provide the information, we provide the warnings, we provide as much information as we can to enable the decision, and the decision has to be taken by the operator. So in the aviation sector, they are getting very ready, and probably they're the most, on a readiness level, they're probably the highest prepared sector, at least in the space that I operate in. For this, they are putting in place processes to deal with information from both an air traffic control operations point of view to a pilot point of view. And the information we provide has to be provided in a format that they can use. So the format we provided to the aviation sector, for example, is different to the format we provided to the energy sector. The energy sector is not ready to be able to use the information yet, because they require the lead times to do something with the information is just too long. So it's a work in progress, and we have to keep working with the users and the operators to ensure that they understand the information we provide, what it means for them, and then how long they have to make a decision, which is often not long enough, particularly in a bureaucratic society. Thank you.
Okay, thank you, Leanne. Very good, very good. There's a question in the chat. I don't know if you want to answer it in the chat, but we haven't got time to go through it now, but we'll answer it later one way or another. Anyway, our next speaker is Raffaele Tarone from Italy, and you're going to give us the Italian perspective on this. So here's over to you, Raffaele.
Okay. I just need only. Okay. Okay. Good morning, everyone. I'm Raffaele Tarone, and I will present my master thesis work entitled Event Detection and Parent Identification for Low Earth Orbit Fragmentations, developed together with the SST team of Federico II University of Naples. Above all, I'd like to thank all the organizers of the conference for the opportunity, and obviously my supervisor, Professor Fasano. I will start from a brief introduction of the topic, proceeding with an evaluation of the main objectives, a description of the implemented methodology with various test cases and subsequent results, and obviously, finally, I will arrive to the conclusions. We all know that the rising number of space launches in the last few decades determined a dramatic increase of space debris, which represent a growing concern for satellite orbiting around the Earth. Being able to predict and avoid any kind of in-orbit collision or explosion is key to ensure safe and continuous operations of space assets. But obviously, not all fragmentations can be predicted or avoided. Therefore, identifying as soon as possible any active or dismissed satellite or known debris involved in a fragmentation event is a fundamental procedure in order to comprehend the future evolution of a new space debris cloud. At this purpose, a new algorithm implemented in MATLAB has been used to analyze the evolution of a given set of newly discovered fragments with the aim of detecting through a backward propagation the epoch of an originating fragmentation event, and also identify which known objects are involved. This is a representation of a backward propagation applied to the well-known Cosmos-Iridium collision. Speaking about the flow diagram of our algorithm architecture, it starts from a filtering procedure where the fragments that can share the same origin are identified. Then they are propagated backward in time for a given time frame in order to that is long enough to include the event date. Then this fragmentation event is detected. The remaining fragments are clustered based on their orbital elements, and finally each one of them is assigned to the corresponding parent body. Starting from the filtering procedure, the first step is a preprocessing aimed at removing from the initial pool erroneous values in mean motion, eccentricity, inclination, and the drag term B star. This is applied on the two line elements of each fragment, and these errors can be done to the uncertainties in the initial orbit determination process. Additionally, we have two geometric filters that are used to evaluate intersections among the fragments' orbits based only on their mean orbital elements. The first one of them is called the peri-G-apogee filter and is used to delete pairings of fragments which cannot perform close encounters due to a lack of overlapping between their trajectories. In this calculation, we do not include the orbit's orientation and also position of fragments along their orbits. The second filter is the MOID filter, where we compute the minimum orbit intersection distance, and we verify that this distance between two trajectories is below a given threshold. Here we have included the orbit's orientation, but again, we neglect the position of fragments along their orbits. So both these two filters are time independent. Then starting from a common instant, position and velocity of each of the remaining fragments are propagated backward in time with the new update every 60 seconds until the end of the search time interval. For this last parameter, a maximum of 20 days has been considered, while for the mass and the area distributions of fragments, a Gaussian distribution can be used when they are unknown. In the second table, instead, we can see the parameters related to the orbital perturbations taken into account by the UNINA propagator, which has been developed by the Aerospace Systems team of Federico II University. Then we have the event detection phase, where the mean relative distance among each couple of fragments at each time step of the propagation time is calculated using the Euclidean distance, and the time instant when this same distance reaches its minimum value is identified as fragmentation time. Then an additional time-dependent filter can be applied in order to select the fragments that can arrive close enough in order to share the same origin. Then the fragments can be clustered using a similarity function to calculate their deviation in terms of orbital elements, and finally, each one of them is assigned to the corresponding parent body. In this particular final phase, position and velocity of each object are compared with the many candidates once. These candidates are selected based on the possibility of being in the proximity of the fragmentation event at fragmentation time. This whole procedure has been tested on 4 different cases, 2 simulated and 2 real events. For the simulated explosion and collision, they are modeled through the NASA standard breakup model, and the resulting clouds of fragments are propagated initially forward for 14 days, and then they are entered inside of our algorithm. In order to test the effectiveness of the filtering procedure to the initial fragments, we can add a given number of additional fictitious fragments, fictitious objects. Then for the real cases, we have selected the explosion of the dismissed satellite NOAA-16 and the Russian anti-satellite test on the dismissed satellite Cosmos 1408. Obviously, the most relevant results will come from these real events, but the simulated data have been fundamental to understand the effectiveness of the code because, for example, speaking about a priori information, we know that parent bodies, event place and time, the total number of fragments, the number of fragments coming from each parent fragment and also their area and mass distributions are all known parameters for the simulated cases, while for the real ones, they are only, as part of them is only estimated. Speaking about results, we can see in these two plots the correct individuation of the fragmentation event. We can see that this is represented by the minimum of these two curves, which define the trend of the mean relative distance among every combination of pair of fragments for the Earl search time interval. Obviously, this applies for the simulated and real explosion, but obviously for also for the simulated and real collision. Then here we have plotted instead the difference between the position of the cloud's center of mass and the parent body's position at fragmentation time for the whole search time interval. And obviously, again, the minimum of this difference is achieved at fragmentation time for the simulated and real explosion and also for the simulated and real collision. After the simulations, sensitivity analysis has been performed to evaluate the effect of the variation of fragments' ballistic coefficient on the main results. All the propagations at this purpose have been repeated with an initial increase and a subsequent decrease of the area to mass ratio of each fragment. We can see in this plot that for the simulated cases, we can underline a precise trend. In fact, an overestimation of the ballistic coefficient of fragments seems to lead to a lower error, while for the real cases, it was not possible to underline a given trend because of a larger uncertainty on the input data. Okay, concluding, I can say that with the filtering procedure, we are able to identify more than the 95% of fragments originally involved in the breakup event. The fragmentation detection phase works correctly since the breakup time identified corresponds to the actual event date with a relatively small margin of error in the order of minutes for the simulated cases and in the order of hours for the real events. The parent identification process works correctly since each fragment is assigned to the correct parent body. And also thanks to the sensitivity analysis, we are able to understand that an overestimation of the ballistic coefficients of fragments can take to a smaller error on the various parameters. Thank you for your attention. This was the end of my presentation.
Thank you very much, Raffaele. Do we have any questions here? I have a question. So your 20-day duration, is that due to the TLE errors? Yeah. It is. I wondered. You were going to say.
Yeah, the 20 days parameter has been considered because we have to take into account the fact that after a fragmentation event, there is the need of some days to have an initial orbit determination process on the fragments. So they need to be detected, classified, and then they can be entered inside our catalogs. So it depends on when information related to the fragments orbits are classified, and we can take them above the catalogs. Yeah, from the catalogs.
So is there any hope to go beyond 20 days if you had more? There is. So you could identify relatively historic event. Okay, very interesting. Very interesting. I bet governments are trembling at all that. Okay, moving on then. Thanks, Raffaele. Thanks for coming as well. Luke, where's Luke? I didn't see you right in front of me. So Luke's important to us because you're partly funded by GNOSIS, and Luke is at the University of Kent. What year are you in?
I'm in the final year of my PhD, my third year of my PhD.
So this should be a good talk then. Over to
we can hope.
I'll tell you what.
That would be excellent. Would it also be possible to get a glass of water from the standby team? Correct. Thanks, Don. Okay. So my name is obviously Luke Cornwell, and I'm a university student at the University. I'm a PhD student at the University of Kent, and as you said there, I'm partly funded by GNOSIS. Today I'll be talking to you about small satellites for sustainability in space, and from space for that matter. So when I say small satellites, really I mean nanosats. I'm talking about the small stuff up there. I'm talking CubeSats and things kind of under 10 kilos in mass. Jordan gave me a very good introduction there to problem of altered debris and the different things that are causing large creations of small particle fragments and so forth. This plot here shows object count against time and basically describes how rapidly it's increasing. As you can see, it's very rapid indeed in recent years. This graph with altitude against particle diameter, so that's altitude on the Y, particle diameter on the X, we can see that for anything under 3 millimeters in size, we need in-space detectors or in-situ detectors to actually detect these particles because they cannot be observed from Earth. So that's very important to this talk and the idea of using small sats. Okay, so firstly, let's talk about sustainability on Earth, because when you say sustainability, the first thing that pops to our mind is Earth sustainability and the climate crisis we face down here. So satellite data provides over 50% of all climate data and half of the 50 essential climate variables. So that alone would suggest that keeping space available to use would be a good reason to keep space sustainable as well. But small sats have a range of different specialized things that are quite unique to them. The main one is their increased temporal and spatial resolutions, which coming back to a question we just had in the last talk, 2 talks ago even, you can use them for things such as flood detection in near real time because much better spatial resolutions. So that's how we're using them for sustainability here on Earth. But there's also been a lot of research on them for sustainability in space. It's all part of the big small sat revolution that's kind of happening in and around us at the moment in the space industry. Here's a list of different missions that are in space and or in development, and they are all using CubeSats or CubeSat-sized satellites. So are small sats big enough? That's all well and good. Small sats, yeah, they're cheap and they're relatively quick to market, so that's big thumbs up. But traditionally, we've always been looking for large areas. For a 3-year mission at 7 to 1,000 kilometers, we traditionally consider a 1 meter squared being the minimum kind of area you can expect to use for a detection surface. Obviously, CubeSats are much smaller than this. And the idea would be, if we want to use these as valid kind of orbital debris detectors, we'd need to get large areas by accumulating over many, many CubeSats. But can you do that? Will this actually work? In reality, and will the statistics work out and come out? This is something I plan to answer with this set of research. And what I did was to compare space exposed surfaces of small size, small spatial areas, to the orbital environment models and predictions from models such as MASTER and ORDEM, but in this particular case, MASTER. So I used a tray from the LDEF mission, which I'm sure we're all relatively familiar with. It was exposed for 6 years, and this is tray B9. On this particular tray, there were several different plates of varying sizes. And on the right here, we can see the results from a crater survey on those plates. So while it was in space, it was being impacted by cosmic dust and orbital debris. And the impact survey on the right here shows you the different number of impacts for different sizes over the different plates of different area. If we look at just the stuff smaller than CubeSat faces or CubeSat type sizes, we're looking at things from B9, P3 downwards. And we can see that in a couple of occasions there, we've got quite high fluxes and very low fluxes. All those very small plates that didn't receive any impacts at all suggest there's nothing in space. This is a clear underinflation of the true orbital environment. The same can be said for very small plates that receive one impact, suggesting a flux of near 100, which is again an overinflation. So this is the reason why we wonder, is it possible? Really, you need large surface areas. But if we accumulate across all of those plates, and it gives us something like 0.174 meters squared cumulative area, we can then see we get fluxes of 7 impacts for greater than 500 microns and 2 impacts for greater than 1,000 microns. So now we need to compare these with predictions that we have from our models, which have had lots and lots of data fed into them from large surfaces and collective small surfaces such as tray B9. So doing that, I used ESA's MASTER model, which is a modeling software that simulates the orbital debris environment and also the cosmic dust environments in the low Earth orbit and up to large orbits such as GEO. Okay, so I did that, and this is what you get back from MASTER. If you simulate LDEF's orbits at the time of LDEF's launch in its epoch, and using tray B9 pointer direction, we get this back as a flux to particle diameter kind of plot. So that's the output from MASTER there. Unfortunately, MASTER gives you particle diameter against flux, or flux against particle diameter even. We need to convert that to crater size to be able to then relate it to the data we see on the craters that we observe on aluminium plates. Doing that, I used this equation here, which can be seen in more detail in the reference. And that gives us the plot down here. So once we've applied that to the data from master, we end up with this plot here with flux against crater lip diameter. And on here, we can also see plotted the tray B9 results from that last slide, where I accumulated flux over all areas. And we can see that they fit quite nicely to that curve, which is pretty good. If we zoom in there and take a closer look, on the left here, we have the particle diameters produced by master, which come along with their predicted uncertainties. And on the right here, we have the converted crater lip diameter and the tray B9 fluxes. And as you can see, they would overlap quite nicely with the relevant particle diameters for crater lip diameters in regards to uncertainties. So this would suggest that you can get meaningful statistical data by accumulating over large numbers of CubeSats and increasing area that way. Okay, but the greatest strength of CubeSats is that they're really quick to launch. This means you can use them for great things such as observing floods and wildfires and things for Earth. You can also do this for observing things such as fragmentations in LEO. So you can send one up into a known orbit where you just had a fragmentation and you can sample the small particle population. Problem with that is you'll only be able to launch a few at one kind of time, because usually you need to look for right shares and so forth. So that means you're not going to have a large enough area, not going to get statistics. The solution to that is use novel techniques that increase your area. So you send it up there with one of these many types of techniques that are in development and increase your area without increasing your drag, hopefully, for your space weather guys out there. And then you can sample that breakup and the small particle environment ensuing from said breakup. Okay, so the conclusions there are CubeSats are great for capacity building because they are cheap and quick to market. This means they're also being quick to market. You can enable investigations for sudden events such as fragmentations. So if we don't want to just see what the big stuff's doing and where that came from, where it's going, we want to see how many small particles are produced as well. This is the kind of thing you could launch in a heartbeat because it's relatively cheap. You can go into the shop on Monday, literally a CubeSat shop, buy a CubeSat, attach an instrument to it, give it to a launch provider, you're in space. So that's excellent for these kind of things. Obviously, to do that for a reactive launch, i.e., this is the bottom point, you ideally need to increase surface area because you won't be able to get enough satellites up there in time in close enough proximity. But the key takeaway is that by investigating space exposed surfaces of relatively similar sizes to CubeSats and or smaller, it would suggest that accumulating area over large amounts of CubeSats or large numbers of CubeSats would in fact lead to meaningful statistical data and could be used as a potential source for valuable data for things such as our models and other information. So thank you all very much for your time. I'd also like to thank the University of Kent and GNOSIS for my funding and for my PhD. And yeah, if there are any questions, I'd be happy to take one and probably pick up the rest afterwards in chat.
Anonymous. This is one way of losing weight, isn't it?
Hello. So I was just wondering, how many CubeSats would you have to get reasonable amount of like statistics in a given orbit or for a given like orbit range?
Great, thanks, Don. Yes, a very good question, Aisling. However, yes, regarding that, if we looked at the grid table there, we had 0.174 area there, and that gave back relatively good statistics. Obviously one case, but that would be equivalent to 17 1U CubeSat faces. So you could get that from something like 4 CubeSats in entirety, or 17 smaller satellites with one face given over to orbital debris detector, or even using a larger satellite with a small detector placed on it for known relative mass cost, because it's very small mass compared to a 1,500 kilogram big satellite. Similarly to that, though, in my supplementary slides here, I have timescales for impacts and so forth. If we look at this one, for things at the 100 micron kind of range, we're looking at, what are we looking at, 10 to the 4, that's 100 microns even. We're looking at something like once every 10 days for one face for varying sizes of CubeSat. And then we're looking at, again, 3 to 5 days or so for if you look at the whole CubeSat, if it's being shot from every angle. So yeah, realistically, it'd happen quite quickly. For the very, very large stuff, which is always relatively rare, this looks quite big. But if you were to put up 100, say, which is relatively easy, bearing in mind Elon Musk puts up 60 of those Starlink things at a time, and they're huge. So you'd be able to get 100 up there in one of those kind of launches in one go. That would, take a factor of 100 off of this right-hand column for days per impact, and you'll be down into counts of years for even a millimeter impact. So promising, it'd be quite handy. But yeah, the larger the better. 17 is a minimum, and hundreds where you want to be looking.
Thanks, Luke.
Great, thanks, Tom.
It's all right.
Thank you. Thanks, Luke. So moving swiftly along to our next session, we're going to sort of move from understanding the space environment to thinking about policy and law and what policymakers can be doing about it.